All right, everyone. So this is officially the last topic of new stuff that we're going to cover in this Organic Chemistry 1 semester. This is our lab topic. So this is going to be an experimental technique known as nuclear magnetic resonance spectroscopy, nuclear magnetic resonance spectroscopy, more affectionately known as NMR. Much like our IR lecture, this is a topic that can be incredibly complicated. So I wanted to record these videos to sort of like make it very clear what the expectations are in terms of the tiny corner of this subject matter that I expect you to know. Truth be told, people dedicate their lives to NMR. A lot of NMR scientists only do NMR, which is kind of weird for an experimental technique. Most scientists combine multiple ones. NMR is so complicated that once you really get into the advanced levels, you kind of fall into your own rabbit hole. It's incredibly mathematically intensive. It's also very cool and it can do some powerful stuff, but we're just doing this introduction to it. So there's a few skills that I want you to be able to have, and that's what we're going to focus on. But first, let's just introduce this. So again, it is a type of spectroscopy, meaning that you are using photons and their interaction with matter in order to gain information about that matter. So just like, sort of the basic spectroscopy format that we had similar with IR, this is a light bulb. That was pretty terrible. But nonetheless, you take your source of radiation. In this case, for NMR, you're actually using all the way down at the microwave frequency. Remember IR, we were in this frequency here. If this was a visible light bulb, like the type you put in your lamps, you would be in the visible region here. But nonetheless, they're sending out the same thing, which are these photons that have a certain frequency, a certain wavelength, a certain amount of energy, and they're going to be interacting with your sample in such a way that some of them will end up getting absorbed while others end up passing through. Okay, so this is the basic format of all spectroscopy, this interaction between photons and matter. Okay, and again, for NMR specifically, we are talking about the microwave region, so really, really long wavelength, really low energy photons. And again, yes, you're just measuring now the interaction between this electromagnetic radiation. In this case, remember with IR, we were sort of measuring these vibrations and vibrational excitations that we have within the molecule. Here, the interaction comes between the electromagnetic radiation and the nucleus of the atom. Okay, so the protons and the neutrons within the nucleus of an atom. It only works when there is either an odd number of protons and or an odd number of neutrons. Okay, so the famous ones that are used are H1 NMR. So it turns out that most of the hydrogen in the world is only 1 proton, 0 neutrons. So that's most of these compounds, most of those atoms are NMR active. They have that odd number of protons. The other super duper common one is carbon-13 NMR. Those are the two that we're going to focus on. Carbon-13, on the other hand, is not very abundant. Nonetheless, everything contains a small amount of carbon-13, so you can take advantage of that. Or you can go out of your way to make sure that you have this isotropically enriched sample. So meaning that you create your molecule in the presence of only carbon-13 atoms. There are other ones that are also used in more advanced levels, but again, we're going to focus on these two, the carbon and the hydrogen. And actually, we're going to focus on carbon first because it's a little bit more straightforward. So how exactly does this work? This is something that's really kind of difficult to picture in your mind, but just bear with me here. So each one of these arrows represents a nucleus. So let's just say it's an H1 nucleus, okay? These things have this property called spin, which means that they have this angular momentum. How we like to think about that is to imagine, much like you have a top or a dreidel kind of thing that you spin, that's what's happening to these protons as well. Okay, so they're sitting there and they're spinning. They have this sort of angular momentum associated with them. In the absence of any magnetic field, there's no rhyme or reason to where these things are pointed, right? So they're just spinning around like a top in any direction. As soon as you apply a magnetic field, those protons will align themselves such that their spin is either parallel to that magnetic field or it's anti-parallel to that magnetic field, right? So you turn on a magnet and all of a sudden all these protons will align themselves in such a way that they're spinning either against or parallel to this magnetic field, okay? So this means that NMR has to take place in the presence of this applied magnetic field. So then what happens? Well, it turns out that the ones that are whose spins are aligned against the magnetic field are slightly higher in energy than those whose spins are parallel to the magnetic field, right? So again, they're all spinning every which direction. You apply this magnetic field, all of a sudden, some of them align in this low energy spin state that's parallel to that magnetic field that goes in the same direction. And then you have the other ones that are aligned in the exact opposite direction, which are slightly higher energy. Okay, so the photons that are going to be sent in there that are going to be absorbed, right? Again, that's the nature of all spectroscopy. What they're going to do is they're going to have the exact energy that bridges this gap. And so they're going to be able to kick an alpha spin, one that's spinned directly with the magnetic field. Once it absorbs that photon, it'll be knocked in the exact opposite direction, spinning against, right? So let's say that this H1 proton right here is the one that absorbs the photon. What's going to happen when it absorbs that photon is now all of a sudden it's going to be spinning in the opposite direction, or rather, the spin is aligned in the opposite direction. Okay, so that's why these protons are, or rather the nuclei of these atoms are interacting with this magnetic field at all, is because they've aligned themselves against it, and then all of a sudden they absorb this, or I'm sorry, they've aligned themselves with the magnetic field, and then they absorb a photon and they're aligned against it, kind of flips them around. Okay, and then the other thing that you hear a lot with NMR is, if you hear some NMR scientists, they're always bragging about the size of their magnet. So it turns out that the larger the magnet, the larger that magnetic field that you apply to that sample, the greater the gap is between those two spin states in terms of their energy. Why this really matters is the larger your magnet, the cleaner your signal is, okay? Because there's nice big gaps in energy between these between these spin states. What that translates to in the spectrum is that all your peaks are nice and neatly separated as opposed to being all bunched up and sitting on top of each other. So bottom line is the better the magnet, the stronger the magnet, the better resolution you will get in your NMR spectrum. And then just to give you sort of an idea of what an NMR spectrum looks like, this is one here. This is for proton NMR, otherwise known as H1 NMR. And so this is the kind of information that you get. So first of all, let's just kind of take a large view look at this here. On the bottom, you have chemical shift in terms of ppm. This is frequency, much like the frequency of a photon. It's always measured to this special compound TMS. So whenever you do these experiments, you have a little bit of this TMS in there that gives you a signal. You make that 0, and every other frequency you get is going to be measured relative to where that TMS peak is. Okay, this is kind of just practical stuff. It doesn't really, it's not all that necessary to understand when we go to analyzing these spectra, but nonetheless, in terms of like, if you were to do this experiment, important to understand. And then notice that unlike our IR spectra, here we have these peaks that are all pointed upwards, okay? And so the whole goal is going to be to look at a spectrum like this and get as much information from it as we can in order to determine what our compound was, or to maybe match it from a list of possible compounds. And so we'll get into why this looks the way it does. Just real quick terminology. There's some weird terminology here in terms of upfield and downfield. Notice that downfield corresponds to a larger chemical shift, and upfield corresponds to a smaller chemical shift, kind of backwards from what you would expect. Okay. I'm not going to go too far into it, but it has to do with like why an atom will shift relative to where it does. Has to do with what's called shielding. Basically, there are some complicated electronic effects. For example, a pi bond that can lead to shielding of a proton's nucleus, and thus make it shift either further upfield or downfield. Okay, we'll sort of match functional groups to where they absorb in terms of chemical shift. But yeah, I don't want to go dive too deep into the theory behind it, because frankly, you don't need to know it for the ACS exam, and it gets really complicated really quickly. All right, and then just to look another sort of few last considerations in terms of the solvent that you use, right? Again, hydrogen 1 is NMR active, and it's everywhere. If you pour yourself a glass of water, 90%, more than way over 90% of the hydrogens in there are H1, and so they are NMR active. So whenever you use a solvent, you have to make sure that it's either doesn't have any protons at all, or it's deuterated, meaning that you're using a special hydrogen isotope. This D stands for H2, or the deuterium isotope. You hear my roosters going here. So then the last sort of thing, again, I mean, so we cool this magnet down with helium. It has to do with how well the signal passes through it. Don't go into that. Again, the other important feature here is that you have this giant magnet. And so you'll see NMR devices have these giant magnets. And again, the strength of that magnet corresponds to the strength of your signal. But this sort of core right here represents a cylindrical kind of magnet. And then you stick your sample right in the middle. Then you're going to send in some frequency of photons. You're going to measure how much comes out. That's the basic of it. We can get a little bit more complicated from there, but that's just kind of the basics of NMR.